Hi guys. Sorry I couldn't be with you today, but you've got virtual me, which might be better, might be worse. Who knows? So I want to go over this little practice quiz that you just took or took last night for homework, depending on which class section you're in. Um, the quiz that you'll be taking on projectile motion and vectors is going to look very similar to this. 3 questions, right, about dividing vectors into components and applying that skill to projectile motion. So let's go ahead and get to this, right? First question is about Kevin. He kicks a soccer ball at a 25-degree angle with a velocity of 7.5 meters per second. And the question asks, what are the horizontal and vertical components of his velocity, right? So start off with a little picture here. Right? We've got his original velocity, which is 7.5 meters per second. Right, and then we know that that was at an angle 25. And our question here is about the horizontal component, right, which is side to side. Imagine that's a straight line, right, and our vertical component, which is up and down. Right, so this is going to be Vy and Vx. So lucky for us, right, when you divide any vector at an angle into its components, right, this is going to be a right triangle, right? So we can use some trigonometry, right, a little SOHCAHTOA, to determine what our components are going to be, right? So for Vx, right, Vx is adjacent to our angle, right? So we're going to use cosine, right? Vx divided by the hypotenuse, which is V, 7.5, right, is going to equal the cosine of the angle theta, right, which is this angle here, right? So if we add we're going to multiply both sides by V, right, and I'm going to go ahead and jump in and add our numbers in there, right? So our component in the horizontal direction is going to be cosine 25 times 7.5. Right? Go ahead and break out your calculator. Super important, right, that your calculator is in degrees, not radians. If it's in radians, sometimes you'll get a negative number, which is going to be super confusing. So I got, when I did this out on my calculator, Vx equals 6.8 about meters per second, 6.797, right? I'm going to round that to 6.8. Cool, like it. To solve for Vy, right, we're going to use that as opposite of our angle that we're given, right? So we're going to use Vy over V equals sine theta, multiply both sides by V, right? We're going to get Vy equals sine theta, which is 25 degrees times 7.5 meters per second. Plug that into your handy dandy calculator. You should get Vy equals 3.169, 3.2 meters per second. Call it. Okay, so that's what I got. Feel free to fight me on it, but I think that's right. And that's what I'm going to use for number 2. Right, number 2 says for the same soccer ball in problem long. I'm assuming that I meant problem 1. Sorry for my typos, guys. Problem 1. How long is the ball in the air? How far from the kicker does it land? So there are two questions here. One is how long is it in the air, right? So in this one we're looking for delta t, right? And how far from the kicker does it land, right? We're going to look for delta x here, right? So we have, right, we just solved for, I'm going to write them down here, Vx, right, we've got its velocity in the x direction, and we've got its velocity in the y direction, which was 3.2 meters per second. So we've done some of the hard work here, right? So this is a projectile that's kicked at an angle, and we've already found each component, so that makes our lives a little easier. And I'm going to go and just write out our little schema here. Remember, In the x direction, we follow constant velocity. In the y direction, we follow constant acceleration. And these two things do not affect each other, right? They don't affect each other. We can treat them individually, right? We've got Vx equals 6.8. We're curious about change in time, right? That's a question that we've been asked, and we're curious about change in x, right? But we don't have enough information in the x direction to solve for either of those things, so we're going to go over to our y direction, right? We've got Vy, right, is going to be positive 3.2 meters per second. Acceleration, it's in free fall, so that's going to be negative 9.8, right? And assuming that the ball lands on the ground and the ground's the same height as where it started, delta y is going to be 0, right? 0 meters. We don't have delta t, but we can solve for it, right? We can use delta y equals vyt plus 1/2 acceleration times squared. Go ahead and plug some numbers in there. 0 equals 3.2 times plus 1/2 negative 9.8 times squared, right? Gonna do some algebra here. Watch your signs, right? And watch your order of operations, right? That was a big thing that we talked about earlier that can trip some people up, is making sure that you're following some basic algebra stuff here, right? So I'm going to divide both sides, right, by negative 4.9t, right, because they have that in common. I can divide it by a number, and I can get rid of one of my t's here. And I'm going to get about 0.65 equals t, right? So that's 0.65 seconds, right? Because I divided by time, so I got rid of one of the t's, right? Remember, time squared equals time times time, right? So, cool, I answered the first part. Ball's in the air for 0.65 seconds, a little over half a second. Now I want to turn my attention to this change in x, right? And I know that in the x direction, right, Vx equals change in x over change in t, right? So I can go ahead and say Vx times change in t equals displacement, change in x, right? 6.8, that's the number that we calculated before, right up here, times what we just calculated for delta t, because it's in the air for as long as it's traveling horizontally. Go ahead and do some little calculations there. And you're going to get that the ball goes 4.42 meters horizontally. So kind of a lame kick, Kevin. Gotta work on that a little bit. But yep, that's what I got. Feel free if you've got any questions on that. If I did my math wrong, it's happened before. And then let's check out this last question here, right? So Seth is on a dirt bike. He's launching himself off a cliff. This should be a fun one to draw, right? Here's my cliff. Here's a dirt bike. Right, there's Seth on his dirt bike. It's a really lame bike, right? But he's launching himself exactly horizontally, right? He has no vertical velocity. And he's going 16 meters per second. And the cliff, we're told, is 10 meters tall. So he has 10 meters to fall, right? And he's going to sort of, do one of these. All the way down to the ground, right? And what we want to know is how far horizontally does he travel before he lands, right? We're curious about this distance here. All right, so where do we start, right? Good place to start is to write, what do we know and what are we missing? So in the x direction, right, we know we follow CVM. We have actually our Vx, right? his initial velocity of 16 meters per second is all going horizontally, none of it's up or down, so we can use that as our Vx. We don't have delta t, and we don't have delta x, right? And delta x is our big question mark, right? That's going to answer the question. But we need to find delta t in order to find delta x. So we'll go ahead and see what's up in our y direction. Again, we're following CAM. Our Vy, right, is 0. Initially, he has no velocity, right, up or down. He only has velocity horizontally when he leaves the cliff. He's going to gain some vertical velocity, right, as he falls, but initially he has none, right? That gain in vertical velocity comes from his acceleration, which is in free fall, so it's negative 9.8 meters per second squared. Our change in y, right, to get from this point here down to this point here, he's got to fall 10 meters, right? So his change in y is going to be negative 10 meters. Right, he falls 10 meters. So we don't have delta t, but that's okay. We can solve for it, right? Using change in y equals velocity in the y direction times t plus 1/2 acceleration times squared. So that's going to be negative 10 equals 0t plus 1/2 negative 9.8 times squared. So negative 10 equals negative 4.9 times squared. You're going to get negative 10 over negative 4.9 equals times squared. That's going to be 2.04 equals times squared. Go ahead and take the square root of all that, right? Remember, this has to be your last step, that square rooting. If it's not, then you're probably going to get the wrong answer. And your answer is time equals 1.43 seconds, right? So that tells us that he's fallen through the air for 1.43 seconds. Now we can go ahead and check out in our x direction, right, what's going on here, and how far does he travel over that time, right? So our velocity x times change in time is going to equal how far he travels. He's going to go 1.43 seconds times 16 meters per second. And that's going to give us a displacement of 22.9 meters that he traveled. Okay, so that's our practice quiz. You can count on our actual quiz looking a lot like this. So if there was anything in here that was tricky for you, I'd encourage you to go ahead and review your notes from the past classes. And talk to a friend, right? There are definitely some people in this class who are getting this down pat, right? See if they can explain it to you, because that's going to help them and it's going to help you, all right? So let's file those away for now. That's going to be your homework, right, to study for this quiz and get a handle on this stuff. But I want to sort of move on to our next big adventure, which is gonna be forces, and I want to run through just some basic information on forces before I let you guys go. Let's see if this will, there we go. Depending on what class you're in, you may have seen this before. If you are in Block 5, you guys haven't seen this before, so you may have to pause on some slides to get all of the information down. I'm going to go through this quickly because Block 4 has seen this before, but once I get through it, if you want to click pause on each slide so you can get down the information, I would highly recommend it. So, Star Wars pun, may the Force be with you. We're about to talk about forces, which are a huge piece of this sort of physics study. You may be asking yourself, what is a force? Well, a force is generally something that causes a change in motion. and it's measured in this Newton's unit. No big shocker, that unit is named after Sir Isaac Newton, who played a huge role in the discovery of these forces and sort of defining what they meant to the physics world. You can't see forces, but you can certainly feel them. In some cases, you could perhaps see them in airflow, but for the most part, they're more of a feel thing, right? So generally, a force is something that causes a change in the motion of an object. You guys had a homework assignment where you looked at free body diagrams, right? These are how we sort of represent forces acting on a system, right? So you sort of draw the system as a particle, and then the forces are shown as a vector, right? They have magnitude and direction, and they show the direction that the force is acting on the system. So for example, this system is a ball hanging by a wire, right? So in its free body diagram, right, the force of the wire is pulling up on that ball, right, keeping it suspended, while the force of the earth, otherwise known as gravity, is kind of pushing down on that ball, right? And these two forces are what we call balanced, right? They equal each other. They're balanced, so the ball will sort of stay where it needs to be. If they weren't balanced, the ball would be moving, but we'll get there in a second. So there are a couple different types of forces. We talked about them in our past video. We talked about contact forces, right? These are forces that are communicated when one object touches another object. Within contact forces, there are a couple different types of forces. So if you're in Block 5 and you didn't get these down, don't worry, you haven't seen them before, but now would be a good time for you guys to pause the video and go ahead and write these all down, because I'm going to kind of blow through these and give you sort of examples of each, right? So frictional forces happen when two objects are kind of sliding over each other, right? When one object moves over another, friction fights against that motion. It's a force in the opposite direction of motion. Tension forces are transmitted through ropes or cables. They're pretty straightforward, right? Anything that sort of can hold what you would think of as tension probably is exerting a tension force. Normal force is an odd name for something that happens every day. It's the force exerted upon an object when another object is in contact with it. For example, there is a normal force that you are feeling right now from the chair you're sitting on, right? It's the force up from the chair that's fighting gravity. Same thing with, your textbook sitting on your desk. It's feeling a normal force upward from your desk. Applied force is sort of this general term for any force that is a contact force but doesn't fall into any of these categories, right? Like, me pushing the textbook off the table. That's an applied force. You could also call it a normal force, but when it's consciously applied by something else, we like to give it another name. Spring force is any force that's exerted by a spring, right? So these are all different forces that could happen through contact. Our next example of a type of force is field forces. There are three main field forces: electric force, magnetic force, and gravitational force. Electric force and magnetic force, we'll talk more about these later in the course. I don't want you to focus too much on them. Gravitational force is going to be the big one that we talk about, right? So field forces can be communicated without touch, right? We all feel gravity, but we're not necessarily like constantly in touch with the mass of the Earth or the moon or other large things, right? So gravitational force is a type of field force. Forces, and again, another slide that if you haven't seen it before, you may want to pause. Forces are vector quantities, right, that can be added to each other. And I'll show you an example of that in a second. But, think about when we were adding different velocities together, right? They get added head to tail, and they have a vector sum, right? The vector sum of all those forces is called a net force, right? Or F sub net, you can see that here. And that's sort of a term. And don't worry too much about this bit right now. Write it down if you want. We're going to get there, right? And you had a reading about this the other night. I know it's been a little disjointed, but if F net on an object equals 0, the object has no acceleration, right? If there's no net force on an object, it's not accelerating. But if there is an F net, a net force on that object will have some acceleration that is greater than 0, right? So there's this idea, right, of forces being balanced or unbalanced, right? And what does that mean? How can forces be unbalanced, right? Well, that's really when we look at a system, whether or not forces can be balanced or unbalanced. So here we have two objects, two different free body diagrams, right? This is the one we originally saw with the ball on the wire, right? And remember I said that it was balanced, right? And that means that there's no F net, right? Therefore, it will follow constant velocity model, right? It has 0 acceleration. And if you think about it, right, if you added these vectors, right, F earth to F wire, right, added them head to toe, they would exactly equal each other, right? And there would be no F net, right? So they're balanced in that way. There's no F net. Now for this free body diagram, right, there is an F net. And we call this an unbalanced system, right? Because the forces do not cancel each other, right? Therefore, there is an F net, right? Because if we were to add F earth to F wire, right, head to tail, because F wire is greater than F earth and in the opposite direction, we're going to have some F net, right, in this direction here, right? And that F net, right, is going to indicate that there's some acceleration, right? So what I would like you to do is just take a minute and in your notebook, draw these two free body diagrams and go ahead and try to add them together, right? Add the vectors together and draw an F net. Go ahead and pause the video while you do this. Alright, so, right, you might have something, for the first free body diagram, if you add them together, right, head to tail, you're gonna get something that looks like this, right? You stack them directly on top of each other, they're the same length, there is no F net, right? But for the second one, right, this is the F of the wire, and here is the force of the earth, right? Force of the earth is a little smaller, so you're gonna get, I'll show this in orange, some, right, F net here, right? And that's sort of what we're curious about, right, is this F net. Right. So, right, remember, this is balanced and this is unbalanced, right? So in an unbalanced system, you have F net. And in a balanced system, you have no F net, okay? So what I would like you to consider right now is I've told you that in a balanced system, right, in this system, we follow CVM, right, constant velocity model. And, right, that's because the acceleration equals 0. I just stated that as a fact, right, during our slideshow, that when the forces are balanced, there is 0 acceleration, right, therefore it follows CVM. So, in a system where forces are balanced, can the object be moving? Right? Could the object be moving in a system where forces are balanced? That's my question. So go ahead and take a minute and just jot your answer to this in your notebook. Can something on which the forces are balanced be moving?